Thank you. Yeah, it's always great to be back at summer school. So I'm Maren, and I work for Amazon, which I forgot to write on the slide. And I'm gonna talk about Bayesian quadrature. So the talk will be roughly split in half. The first one is more in the style of a GPSS talk. For those who don't know about Bayesian quadrature, I'll give an introduction. And the second part will be about a paper that one of our interns did with us last year at Amazon. I feel a bit funny with this monitor in front of me, but I guess it's okay. Okay, so let's talk about expensive simulations. So this is a picture of a black hole, and the black hole is in the middle. And you don't see it because the black hole has an event horizon, which is defined by the Schwarzschild radius. And anything that goes inside this radius cannot escape. So any trajectory that light does will always curve back and go back inside the black hole. And what you see outside here in the horizontal plane is an accretion disk. And the picture of it is distorted because a black hole is very massive and it warps the space-time. So what you're actually seeing, so an accretion disk is basically just material that rotates around a black hole on a plane. And what you're seeing at the top and at the bottom is kind of images of this accretion disk that bend from the top and the bottom from this accretion disk. So it's because of this warping of the space-time, it's like looking at the back of your head. So the light basically comes from the accretion disk and kind of goes in front of it and also below. And this picture was actually done for the movie Interstellar. It's a large simulation. They try to be very physically accurate, and they hired physicists because they needed a custom simulation to accommodate the high resolution of the IMAX screen. So this picture also includes some IMAX camera lens flaring, for example. But it doesn't matter. Let's say it's just an expensive simulation, and you're a researcher who wants to use it to learn something about this black hole. So you might be interested in some physical property, or possibly also about how exactly this black hole warps the space-time. So you might be interested in the light trajectories. And so you're going to run the simulation, and it might take a day. It's just very expensive. So sometimes there is a caveat because you don't exactly know what you should input to the simulation. For example, you might not know all the you might not know the properties of the black hole precisely. You have an idea about the mass, but just in a certain range. Or you're not completely certain about, let's say, the chemical composition of this accretion disk or something like that. So what you would do then possibly is you want to compute an expectation over the output. And an expectation is simply an integral. It's a weighted sum of your possibilities. And this is an integral. It might be simple in the sense that it's low dimensional. It might be one-dimensional, two-dimensional, or higher dimensional. But it might still be really hard to solve because your integrand here, f, which is the output of the simulation, so you put some stuff in, you get some stuff out, is just not very accessible. Let's say you give yourself a budget of 10 evaluations or 20 or 100, and all of a sudden very simple sounding integrals become difficult. Now, as a researcher, what would you want to do? You would say, okay, I have 10, 20 evaluations, and I want to be I'm just going to unplug and think it's this one.
Run out of power, or?
No, no. Okay. Okay. Okay, so you have like 20 evaluations and you want to be very smart which ones you choose. So you want to be smart about the alpha here, which ones you input, so that you get a good estimator out. That's one thing, you want to have a good estimator. And the second thing is you already know you will not be very precise with your integral. It's just not possible with so little evaluations. So you ideally would also like to have an error estimate, some kind of uncertainty. The best thing would be a distribution over the answer of your integral value. And that's basically what Bayesian quadrature is about. So let's formalize this a bit more. I motivated the thing with expectations, but you can think of any integral basically. It also doesn't need to be as expensive as a simulation running one day. You could also think about integrands that you can query in a second or two, but possibly you have to solve this integral all the time, like a million times, and then even just a few seconds is too expensive and you're still constrained by the number of evaluations you want to do. So expensive integrals come in different scales. But we kind of assume that your data, so the evaluations, are limited and sampling is somewhat prohibitive. And now the question we want to answer is which alphas do we want to choose to put in here to get answers such that we can solve the integral and get an error. Okay, so I will introduce this in a very similar style than I believe Javier did about Bayesian optimization. He does this introduction really well and I love it, so I'm just gonna copycat him. So this is an intuitive introduction. Let's say we have a function and we want to integrate, it's one-dimensional, and we want to integrate it between -3 and 3. And I'm gonna show you 3 points. And then I can tell you some other stuff. For example, the function is smooth, maybe very smooth, and also I can give you some kind of variability, like Lipschitz constant or something like that. And then probably people here, if I ask everybody individually, you would be able to tell me some value that you think might be plausible for this integral. And so let's say I ask one of you, and in your mind what you will probably do is you will put some kind of regressor through those points and then try to estimate the curve or the area under the curve of this regressor. So if we ask the first person, you might be doing something like this. And on the right side now, this is supposed to be a histogram, so we have one value of the histogram, of the integral histogram. And then we ask a second person. In this person's head, the regressor looks a little differently, and we have a bit of a different integral value, and we can just keep going and ask everybody in the room. And we will just collect more integral values. And this is when we ask 100 people who have 100 different answers, then we will get some kind of distribution over the integral. And they all have in common that they go through these 3 points, because we know them to be true. So now I can ask you, what do you think is the next point we should evaluate? And some people of you might say, oh, maybe here. Some other people might say maybe here in the middle, because we don't know very much about the function. Some would say maybe to the very right side, because it's the most far away from anything we have seen so far. But mostly people will somehow use the uncertainty of this model. So very little people would probably say, oh, let's go here in the middle because we disagree so much over there. So possibly a good place to go would be at a place where people are not sure how to agree on. And one option might be this one. I'm not saying it's the best or anything, it's just thinking one option that people could agree on. And then if we evaluate the function there again, we do the same thing over again. We ask everybody again and get a new histogram over our values. And you can, if you check the histogram here on the left and the right, it actually got a bit more certain. So with each point we get, we kind of shrink also our variance on the integral. So just for people who are interested, this is the ground truth. And even with our 3 points, we kind of got the mean of our distribution here on the right, which is the, I don't remember which one is which, but they're very close together. One is the ground truth, one is the mean of this distribution. Okay, so what just happened? We have built an intuitive integration method. And the essential part of it, that we have taken the integration problem and we have transformed it into a regression problem, which is much easier. We all know how to do regression. We have also incorporated structure into the regressor. I've told you the function is smooth and it has like a certain Lipschitz constant. Knowing all this, we have then expressed our uncertainty in unobserved areas by asking everybody, and everybody had a little different opinion. And then we integrated the regressor model instead. So we integrated each sample individually and plotted a histogram. And this gave us an uncertainty over the integral, which is what we were aiming to do. And then after that, we used all this uncertainty to get the next point. And this may sound vaguely familiar to you. That's also how this kind of typical decision loop goes that you know from Bayesian optimization. So this in words can be written down as a pseudocode, and the pseudocode or this procedure we would then call Bayesian quadrature. So you have a model that you choose to model your integrand, possibly some initial observations, and then you're doing your loop until your budget is full, where you maximize some acquisition function. That's a heuristic which tells you the utility of the next point. You then evaluate at this point that maximizes your acquisition function, and then you take this new observation to update your model and fit your model, and then you do it all over again. Yeah, and in the end you integrate your model to get an estimate of your integral. Okay, so how do we choose the model? And we're at the Gaussian process summer school, so we're going to use Gaussian processes, but these are also the models which are widely used in Bayesian quadrature. So 1 or 2 slides of formulas, Bayesian quadrature with Gaussian processes in a nutshell. So here let's write down the integration problem again. We call the integral z, and I've changed alpha to x. So x is now the input, f is the output. We choose a Gaussian process prior over the integrand, this function here, and we observe at points x, possibly with noise or without noise if we can evaluate the function precisely. Sometimes we might not be able to. For example, if you run a simulation which is based on sampling, your output might be uncertain too. So you sometimes would perhaps want to model noise in here as well. And then, because f is stochastic, z is stochastic as well. And it is distributed Gaussian as well. I'm going to say in a moment why that is. With mean, which is the integral over the mean function of your GP, and variance, which is the double integral over your kernel. So this is univariate because the integral is a scalar. And the nice part is, if you think about the mean function, that's also basically just some parameters multiplied with your kernel. So all this computation boils down to be able to integrate the kernel. And it turns out that you can do this analytically for certain kernels, and one of them is the RBF kernel, or exponentiated quadratic or Gaussian kernel. So if you use this kernel, all these formulas become analytic, and if you know how to do the GP regression, you know how to do Bayesian quadrature. Okay, here's a hand-wavy motivation why we get out a Gaussian over the integral for the distribution of the integral. And it's so you have probably learned during the summer school that Gaussians have certain nice properties, and one of them is that they're closed under linear maps. So if I throw a linear map on a Gaussian variable, you get out another Gaussian with this property here, with the mean, which is the map of the mean, and the covariance, which has the map like multiplied from left and right. And integration is a linear map too, so it's basically a weighted big sum. And so you can write down the joint distribution of your integral and points f and observations y. And then you can use, so observing y is just a special way of conditioning this, or computing a conditional distribution of this joint Gaussian. And you have also learned the formulas in the GPSS. So you take the formulas you know, write down the conditional, and that's the formulas you will get out for the mean and the variance of your univariate distribution over the integral. And I am afraid I didn't write them down here, but you can all do it yourself. Okay, so the next step in our Bayesian quadrature loop would be finding the next point, which is done by an acquisition function. And there are certain different ones out there. Acquisition functions are in a certain way heuristic, so you have multiple options. One way would be to go for some kind of uncertainty sampling, so you would go to the maximum point of variance of the integrand. That's kind of like a local thing because you're thinking about the integrand pointwise. And other acquisition might be to go to the point where that, if you had observed it, would reduce the variance on your integral the most. So that's like a global scheme because you're kind of taking all the points into account because you know the variance of the integral is like also an integral over your kernel. And a third one would be the mutual information, which is the information that you gain if you observe y, or the information you learn about the integral if you observe y. Yeah, so for Gaussians, all of these are analytic, so they sound complicated, but you can just write them down, and they will only depend on the covariance. Yeah, and these last two are also identical in the sense that they share the global maximizer. So the policy would be the same because the location of the maximum is the same. The shape is different, but the location of the maximum is the same. Yeah, I plotted them. So this top plot is just a Gaussian process with 1 and 2 times the standard deviation plotted as shaded areas. And this Gaussian process is conditional on these 3 points. We want to integrate the black function here. That's the ground truth. The mean is in blue. And below here are the different acquisition function I just mentioned. So you can clearly see the difference in between local and global acquisition strategy. The local one is the variance of the integrand, which is maximal on the very right because the variance just grows to the very right. And the other two, which are global, they drop down because the others kind of sum up the contribution you get, or kind of you learn about the other points next to them, while the variance of the integrand does not. So you can decide for yourself what you like better. Okay, this is only the mutual information, and just in illustration how this would work in practice. So you would take a gradient-based optimizer, for example, and optimize this function. The maximum is here, so that's where you evaluate. Then you do you evaluate the point, condition your GP, do the same thing. So you optimize this function here. We're going to evaluate here next, and so on. And in the end, you will basically have learned the integral to very high precision. Okay, there are certain extensions to this. Obviously, you can do all of this in multi-dimensions as well. This is just an illustration. Here would be the true integrand, the mean prediction of the GP, and the standard deviation. And this is the same thing in a 3D plot. So this is when x, the input, is multi-dimensional. But it's the same thing. You just do GP regression with multi-dimensional inputs. Yeah, there's also other extensions. There's interesting work by Roman Garnett's group and Mike Osborne, who do incorporate structure into the GP by transforming it. So for example, if you have positive, you know your function is positive. If you integrate probability distributions, for instance, you can model it with, for example, an exponential transform or a log transform of a Gaussian, or a square transform of a Gaussian process. So this picture here is the square transform. So you would have your GP on the square root of your original integrand, and then you square it. Now the trouble you get is if you square a GP, you don't know how to compute the integral over it again, because you get some kind of chi-square distribution. So the trick there, yeah, kind of that's the additional complication you get if you compare it to Bayesian optimization, for example. There you don't need to integrate your model. And what people do there is you approximate this distribution you get there with another GP, and then you integrate that GP. And that's also not very trivial. Yeah, but so this would be the GP approximation to the transformed GP. And these algorithms in particular have interesting properties because the mean function depends on the function. The covariance function starts depending on the function values as well. So you get some kind of adaptive properties where, for example, in regions of higher mean values, the variance also grows, and in regions of low mean function, the variance goes down. And so it kind of is more like a greedy approach to walking into directions of high function values, and that seems to be beneficial if you go to higher dimensions, because you don't just randomly try to you don't just try to explore your whole space and reduce the variance everywhere. You try to only go to regions where the integral is relevant. Okay. Any questions to the first part so far?
So are there any other kernels that are convenient to work with outside of the RBF?
Yeah, so in Quadrature you are constrained usually because you need to integrate a kernel. I'm only aware of people for multi-dimensional GPs using RBF. There might be other kernels out there. I think Matern might be integrable as well. I'm not sure if someone has done it. However, in one dimensions, there are quite interesting kernels that people do integrate that actually do relate to classical methods. For example, if you think of the Vino process kernel, the min T prime kernel, where the sample paths are Brownian motion, the posterior mean are linear splines, so you get out the trapezoid rule, and so on. So there are some super interesting connections to classic quadrature rules of these like one-dimensional kernels. Okay, second part. Sorry. Oh.
Just a small added question to that: how feasible is it to use a kernel which you cannot integrate analytically Because that would probably be easier than integrating the complicated function you have.
Yeah, possibly. I don't know if someone has tried it. So you would sample the kernel instead, yeah. Okay, so this is a paper we had at UI this year, and it's work by Alex, who did an internship with us last summer. Yeah, so that's Alex and Javier and. Okay, so let's remember our simulation that we kind of used as a placeholder for all kind of integrands that might be expensive. And we wanted to compute this integral. Now let's say possibly you have a second simulation, a simulation which is faster, possibly faster for certain inputs only, and gives you roughly a similar answer. So you might have something like this. And this would still tell you something about the integrand or about the integral, but it's just not precisely the same, possibly because the simulation is not as detailed. You're dropping certain parts. Maybe you have an analytic solution inside of this thing where the other one does some sampling and has like the real mechanism. Yeah, this thing might just drop certain mechanisms that you encoded in your original simulation. Or alternatively, you might think of a secondary simulation as something which is just run at lower resolution. So ideally, you want to integrate the high resolution output, but you also can possibly run the low simulation output. And these other integrands are also called secondary sources. The integrand of interest would be the primary source, and this would be a secondary source.
Sorry? Well, there is something that they missed. So what is P of alpha in this case?
Yeah, I keep renaming x to alpha and alpha to x. So x would be an input to the simulation that you are not certain about.
Yes, I mean P of alpha. So it's a probability distribution?
It's a prior, yeah. So for example, if you know, I don't know, the mass of your black hole is in this region, you might have some prior over this. Yeah, so those we assume are cheaper, and we want to use them to compute our integral. Okay, so the old picture looked like that we had a finite set of alphas, our budget that we can put in here. We wanted to choose them wisely to get some f to compute the integral. And now the situation looks like this, that we have more alphas that we can distribute because these are cheaper. And we would like to know which alphas should we choose and through which simulation should we push them to get answers such that we learn the integral of this left simulation the best. The math is the same. You probably learned about multi-output GPs. There was fundamental work by Mauricio and FX and paper by C et al. Multi-output GPs, and these two relate to Bayesian quadrature. And you consider L sources of your integrand with L equal 1 as the primary source. And then you model all these sources with a multi-output GP, bold F. And the observations, you would just observe an output of one source L at point X. Now, the kernel you can use is an intrinsic co-regionalization kernel, which looks like this. So the covariance would be so the kernel would be the covariance in between a function value of source L at X with a function value of source L prime at X prime. And with the intrinsic co-regionalization kernel, you assume that they factorize in a term that correlates the sources and a term that correlates the output based on the input only. And B would then be a parameter you need to learn. And the math goes the same. You can also again derive the integral over your GP, and you would get a mean, which is the integral over your GP mean, and a variance, which is the double integral over your kernel. And yeah, again, this is analytic if here kappa is integrable, and so you can again use an RBF. This is again the joint. And now this time it looks exactly identical, but this time you have little subscripts here for source L prime and L, and then you would observe just one out of those y's at each time, and then you do your formulas, you know, from how to condition Gaussians and get your answer. Okay, now we need a different acquisition strategy. Before we assumed we need to decide on the input only, so on the axis, the parameters we put into our simulations. Now at each loop step, we need to also decide not only where to evaluate, but also which source to evaluate. So the answer to your acquisition function would be a tuple of the index of the source and a point x. So choosing one of those pictures. And for that, we assign a cost for evaluating source L at x, which is positive, that we assume to know. So an easy example of that would just be assuming that each of those simulations run in constant time, independent of the input, and you know the runtime of the simulation. And then this would not be a multi-source model, but a multi-fidelity model. Yeah, and we would instead of maximizing the acquisition function, we would kind of maximize an acquisition rate. So the acquisition function divided by the cost, and that has some intuitive, or it has some intuition behind it. For example, if A is the mutual information and C would be measured in runtime, then this acquisition rate would maximize the bits per second. So in the total budget we have, we would get the most information in the time we have. Yeah, this is the pseudocode. We basically do exactly the same as before, but the only difference is that when we maximize our rate here, we get a tuple out. Yeah.
In the previous slide, could you come back? From this formula for AL, it seems like you need some proper normalization for C, or you might.
Yeah, it's enough to assume it's bounded away from 0 properly and bounded above. So like, and then you can also normalize it if you want. So you say it's like basically it's like saying you have a minimal cost, so nothing is 0 cost, and you have a maximal cost, nothing runs infinitely long.
And what about how the scale of A corresponds to the scale of C? What if they just match out of the scale of each other?
Could you repeat? I didn't hear.
So, for example, A acquisition function will be in the range from 1 to 2 or something like this, and C will be like hundreds or thousands. So C will matter most, and A will not matter at all.
Mm.
Maybe something
Yeah. So you need to make sure that the rates you compare in between these sources are of the same units, but then the absolute scale doesn't matter because you just compare relative differences.
Yes, so in practice, is there a recipe to do this, to make sure they're of the same units?
So if you would, for example, if you need to make sure that the cost for all sources are measured in the same unit. So for all three, you consider, for example, time as the cost, and not for one you use dollars and the other one time. If you make sure that your units are consistent, then it doesn't matter the absolute scale, because they will always scale by the same value. I want to quickly talk about certain pitfalls that you can do if you extend to rates. I've recapped some of well-known acquisition functions if you only have vanilla Bayesian quadrature, so one source. The mutual information, the reduction of the integral variance. These are monotonic transforms of each other, so they share the same global maximizer. And there are others. For example, some people minimize the integral variance or maximize the negative integral variance, or you can also maximize the integral precision. And usually that doesn't matter what you do because they all have the same maximizer, so you will get the same result. But if you do multi-source Bayesian quadrature, you need to be a bit careful. These two don't work so well. And I will show you in a second why. And I'm just highlighting this because especially the maximal, the minimal integral variance is used quite often. So on the left, I just listed a few common acquisition strategies. They all turn out to be formulas that only depend on rho, which is the correlation between the integral you want to learn and the new observation y. And this is only obviously valid for Gaussians. And on the right side here, I've written down the transforms with respect to the mutual information. So mutual information to itself would be the identity transform, and these are the others, and I've plotted them here on the right side. So on the x-axis you have the mutual information, and on the y-axis the different acquisition functions. And you can see that mutual information is, and what's the blue one? Integral variance reduction, they are 0 at 0. So when the mutual information is 0. And it's 0 when the correlation is 0. So if you don't learn, from your new value, if you don't learn anything about the integral, the acquisition function will be 0 as well. So if you scale it with a cost, it will stay 0. And the other two negative integral variants, for example, or let's look at the integral precision, which is here, this orange one, it shifted away from 0. So I could potentially have a situation where I just lower my cost enough, and I will evaluate at a point which gives me absolutely no information about a model. And then I will get stuck because my model doesn't get updated. I will go back to the same point. So if you generalize to rates, it's not enough to only think about the global maximizer. You need to think about what the acquisition function encodes in practice as well, so like the meaning. And usually a good way to go is to think about that you need to not only encode an absolute value, but some kind of improvement. And the integral variance doesn't do that. It just says, oh, this is integral variance, but it doesn't say how much you learn. Yeah. I think I'm going to skip that. Okay, one-dimensional demonstration of the algorithm at work. This is the Forrester function, which is well known. The Forrester function is in blue, and some kind of secondary source we can assume is this dash line. And below here, I've just plotted some synthetic cost values. This dash line doesn't go to 0. It's just very small here. And on the left side, they have the same cost, and on the right side, the cost differs a lot. And now the acquisition strategy works as follows. So each row is a different iteration, n equals 8, 9, 10. You see the marginal GP beliefs over each function. And on the right side, you like these are the acquisition rates, and at iteration 8, this point here wins, and this point of the secondary source wins, and at iteration 9, this point here of the primary source wins, and so on. So the model switches back and forth in between evaluating secondary source and primary source. Oh yeah, and an interesting fact is that because we encoded that we only want to learn one of the integrals of the primary source, the model doesn't evaluate the green function here, the secondary source, because the cost is the same, so it just goes to the primary source and ignores the secondary source. Yeah, so this is a 2D example, just a linear combination of Gaussians where we drew the weights randomly and the variances at random. And we compared with just vanilla Bayesian quadrature run on the primary source only. And here the interesting bit is that the secondary sources, the middle on the right, are the same cost. And so the model more or less prefers the one in the middle because it's closer to the primary source than the one on the right. It kind of just sometimes goes to the one on the right to check if there's anything to learn. But because the cost is the same, it kind of prefers the one it can learn more about. Okay, last example is a real-world example. So this is the SEER model, SEER epidemiological model. And the SEER model is a model that simulates the spread of an infectious disease. So you have a population of size n, and certain individuals are already infected. And you have stochastic discrete time events of individuals that can change these from being not ill to being exposed, which means you carry the disease but you don't show symptoms yet. And then after a while you will show symptoms, so you will be infected and then you will be recovered. And each transition is modeled by a Poisson process, so you have exponentials with some rate of decay. And the primary source here is the Gillespie simulation, and one query takes about 16 seconds on a laptop because it samples trajectories from the stochastic process, and you kind of need to sample 1,000 or so and then average those to get some answer. So one thing you might ask, for example, is when is the expected height of the infection peak? This is an integral because it's an expectation. And the other one would be when is the expected time occurrence of the infection peak, which is also an integral. And even getting the ground truth here took about an hour on a laptop because each evaluation is very expensive. And we even had to do a Wright-Riemann sum to get it because the Gillespie simulation, although the ground truth function looks very smooth, there's a slight numerical error, and SciPy, Quadrature, out-of-the-box methods couldn't deal with it. But like a right, I mean, kind of, yeah, it surprised us that it didn't manage to do. And the secondary source here would be an analytic model of the same thing. So if for large populations the dynamics converge, or the limit of the dynamics converges to a system of ODEs that do not have an analytical solution, but there are ODE solvers out there and they are much faster. So this would be an example of where the cost is just constant, but you have a large difference. The left side here is the height of the infection peak, the right side the time of the infection peak, and the important lines are this red one, which is the Bayesian quadrature on the primary source only, and the green one, which is like super quick, is very fast to find a good value for both, because it can use the ODE system. Okay, let's recap. So Bayesian quadrature has very exciting applications. Even low-dimensional integrals can be hard. I've motivated with low-dimensional integrals, but there's also really exciting work in higher dimensions for Bayesian quadrature. There are real-world problems out there where the numerical error is non-negligible, so we really would like to model it and propagate this uncertainty. We also want to use structure in the problem, so we like to to put as much as we can into our prior by transforming it or doing other things. This is research which is in its baby shoes still, so there's a lot going. There is still a lot to do, and I personally think that secondary sources are a really cool way to go as well, because you can get more information cheaply. One more word to code. I think the practicals you did was an EmuKit. All the plots I did here were done with EmuKit. It unfortunately only has a very rudimentary implementation of Bayesian quadrature, but I hope that will change, and I would be happy if you check it out. Or also, obviously, pull requests are very welcome. And yeah, thank you.
Questions?
Maybe I missed it. How do you estimate the hyperparameters?
Of the GP?
Yeah, like because now you have this co-regionalization and everything. So
Yeah, so you maximize the marginal likelihood.
in which step of the process?
In the update step. Here, fit model. Yeah, and it's just parameterized such that the matrix is positive definite. You parameterize the. I think it's done in GPy automatically.
So in your experiment with the cost function, do you always know your cost function? Have you looked at problems where you actually want to learn it?
Yeah. So
Most numerical simulations
yeah.
very awkward.
Yeah. So that's a very good question. The super simple example is when you know it's constant, and so you can estimate it at the first run. That would be a very simple example where we did estimate it. But if it gets more complicated than that, that's exciting future work, yeah. So you would try to learn your cost function next to your correlation in between the sources. Yeah.
I was wondering what you assume about the noise processes of your secondary sources. I could imagine them being more noisy than the main, for example.
Yeah. So often you don't have noise in Bayesian quadrature, but if you do, for those, here we assumed the same noise for all sources because it was very tiny. It was more like just numerical noise. Each time you introduce one more parameter, you like there's always a trade-off in between assuming more parameters to have a more flexible model, and but then the model is harder to learn because you obviously already have limited data. So it's a trade-off. But you could think of just having another parameter per source for the noise.
Okay, so that would be perfectly fine to include in the.
Yeah, you can include it in the model, but it doesn't necessarily mean that it works better because you have so little data to estimate all these parameters.
So thanks a lot for the nice talk. I really enjoyed it. There's something else that I missed. How does the model know which source contains the objective truth? If you measure it, it returns to the objective truth, and which ones are, let's say, approximations to the objective truth?
So you mean how does the model know what its goal is, like that it wants to learn the?
So which source yields? So which source yields to the right measurements, and which source yields the approximations to the right?
So that would be encoded in your acquisition rate. That would be like, for example, the information you gain on the primary integral. Right? So that's where it put it in, yeah.
And is this trivial to encode, or?
If you use, so for certain acquisition function, it's very simple because for Gaussians, all of the stuff is analytic, yeah.
A little bit in line with that, so is this essentially your prior, which you specify over like which source is important and which one isn't? And did you consider a case, I'm not very familiar with multi-source Bayesian optimization, but do you consider the cases where you treat all the sources equally?
Yeah, I believe that's done in another paper. This one. So this one assumes you want to learn all the integrals, not just one. I don't think, though, they have an acquisition strategy. They have some kind of oracle that tells you a certain sampling strategy, and that's what they do. So they don't. I believe they don't write on acquisition function, do the active learning.
Okay, so let's thank Maren and Aya again. We've got a lunch break now, and what time?